sulfate, which is used as a fertilizer. And other sulfates and many chemical substances. The steel is dipped in sulfuric acid to remove the iron rust before coating it with enamel. The sulfuric acid is used in normal storage batteries as an electrolyte. Contact process for the manufacture of sulfuric acid. There are three main stages involved in this process. Stage 1. Production of sulfur dioxide. This involves a sulfur burner, a cooler, a scrubbing tower, a drying tower, and an arsenic purifier. In the first stage, sulfide ore or molten sulfur is introduced into a sulfur burner. Dry air or oxygen is allowed to pass from the top of the tower. Here, sulfur burns in dry air to produce sulfur dioxide gas. This hot sulfur dioxide gas is then passed through the cooler, where it is cooled to about 100 degrees Celsius. This cold sulfur dioxide gas contains certain impurities like arsenic oxide, dust particles, moisture, oxygen, etc. This impure sulfur dioxide gas is allowed to pass through the scrubbing tower. This tower is packed with acid-resistant quartz. The incoming gas is washed with a down-flowing current of water. Here, the dust and other heavy particles become moist and settle at the bottom of the tower. Thus, the gas gets free from the dust particles. Now, the gas is allowed to pass through the drying tower. This tower is also packed with acid-resistant quartz. Concentrated sulfuric acid is sprinkled from the top of the drying tower. Since concentrated sulfuric acid possesses great affinity towards water, the impurities such as moisture get removed from the gaseous mixture and thus dries the upward moving gas. This dry gas now enters the arsenic purifier. This tower consists of plates layered with ferric hydroxide powder. The ferric hydroxide powder absorbs arsenic oxide from the gas mixture. Purified sulfur dioxide gas is obtained along with oxygen. Thus, after stage 1, from molten sulfur, we get dry sulfur dioxide gas along with oxygen. Stage 2. Conversion of sulfur dioxide to sulfur trioxide. This consists of a heater and the contact tower. In this stage, dried sulfur dioxide and oxygen are passed through a heater, which contains helical pipes from which hot steam passes continuously. Here, the temperature of the gas rises to 450 degrees Celsius. The hot gas now enters the contact tower. or 4-pass catalytic converter. This tower consists of 4 different passes, and each pass is provided with iron plates packed with vanadium pentoxide as a catalyst and potassium oxide as a promoter. Here, 2 moles of sulfur dioxide and 1 mole of oxygen react in the presence of vanadium pentoxide at 450 degrees Celsius temperature and at 2 atmospheric pressure to give sulfur trioxide gas, and this releases tremendous amount of heat. As a result, the temperature of the gas rises, which converts the sulfur trioxide back to the reactants. To avoid this, the gas is passed through a heat exchanger, where the gas gets cooled to 450 degrees Celsius. This gas contains unreacted sulfur dioxide, and therefore the gas is allowed to enter the second pass, the third pass, and the fourth pass to ensure that the reactants are completely converted into sulfur trioxide. Thus, in stage 2, the mixture of sulfur dioxide and oxygen is converted into sulfur trioxide. Stage 3. Absorption of sulfur trioxide in sulfuric acid to give oleum. This consists of an absorption tower and a dilution tank. Sulfur trioxide gas formed in stage 2 is passed into an absorption tower. The absorption tower is packed with a number of ceramic rings, which act as inert material over which concentrated sulfuric acid passes continuously. Here, sulfur trioxide gas gets dissolved in 98% concentrated sulfuric acid. The ceramic rings increase the contact time between the sulfur trioxide gas and the sulfuric acid. This ensures complete absorption of sulfur trioxide in the acid. As a result, a viscous hot fuming liquid called oleum or pyrosulfuric acid is formed at the bottom of the tower. Sulfur trioxide reacts with concentrated sulfuric acid to give pyrosulfuric acid or oleum. The oleum thus formed is then taken into the dilution tank, where it is diluted with a suitable quantity of water to obtain sulfuric acid of desired concentration. Pyrosulfuric acid reacts with water to give sulfuric acid. Thus, manufacture of sulfuric acid by contact process involves production of dry sulfur dioxide from molten sulfur, conversion of this sulfur dioxide to sulfur trioxide, and finally the production of oleum, which is further diluted to the required concentration of sulfuric acid. Physical properties of sulfuric acid. Sulfuric acid is a colorless, odorless, and a non-volatile oily liquid. When a few drops of sulfuric acid are poured on the blue litmus paper, the color of the litmus paper turns red. This shows its acidic property. The boiling point of sulfuric acid is 338 degrees Celsius. When any metal, for example, copper, is dipped into the concentrated sulfuric acid solution, the metal gets corroded. And thus we can say that concentrated sulfuric acid is highly corrosive in nature. When an electric current is applied to a pure concentrated sulfuric acid solution, it is observed that the current does not pass through it. Hence, the concentrated sulfuric acid is a non-conductor of electricity. While, when an electric current is applied to a dilute sulfuric acid solution, it is observed that the current easily passes through it. Therefore, we can say that the dilute sulfuric acid is a good conductor of electricity. Sulfuric acid is a powerful dehydrating agent. Water should never be added directly into the concentrated sulfuric acid, because by doing so, water may suddenly convert into steam and cause acid to splash. Therefore, when the concentrated sulfuric acid is to be diluted, the acid should be added to water, not the other way around. Chemical properties of dilute sulfuric acid. Reaction with metals. First of all, let us look at the electrochemical series. It shows the reactivity of various metals. Acid do not react, but metals lying above hydrogen in electrochemical series like zinc, when added to dilute sulfuric acid solution, liberate hydrogen gas. Zinc loses 2 electrons which are accepted by hydrogen ions, forming zinc sulfate and hydrogen gas. Reaction with metal carbonates. When dilute sulfuric acid is added to metal carbonates like sodium carbonate. It forms aqueous sodium sulfate and carbon dioxide gas is evolved. Sodium carbonate plus dilute sulfuric acid gives sodium sulfate plus water plus carbon dioxide gas. Summary: metals lying below hydrogen in electrochemical series do not react when treated with dilute sulfuric acid at all. Metals lying above hydrogen react with dilute sulfuric acid. Chemical properties of concentrated sulfuric acid. We all are aware that sulfuric acid is a versatile chemical used widely in various industries like fertilizers, dyes, pigments and plastics. Is H2SO4. The presence of two replaceable hydrogen ions in it indicates that sulfuric acid is a diprotic acid. Now, take some carbon powder in a test tube and add a few drops of sulfuric acid to it. Sulfuric acid gets reduced to form sulfur dioxide, water and nascent oxygen. Due to the release of nascent oxygen, concentrated sulfuric acid behaves as a strong oxidizing agent. This free nascent oxygen further oxidizes carbon to carbon dioxide. Concentrated sulfuric acid has a strong affinity towards water. To understand this property in detail, take some sugar in a beaker. Sugar is composed of sucrose molecules. Add some concentrated sulfuric acid to it and stir. After some time, the mixture turns yellow and then black. Suddenly, a large black mass starts emerging from the beaker. Actually, what happens is that concentrated sulfuric acid drives out water from the sucrose molecules in a highly exothermic reaction. The heat generated causes the water molecules to escape out as steam. Some carbon dioxide and sulfur dioxide are also formed in the process. Thus, the black mass is nothing but carbon escaping the beaker along with the steam and other gases. This experiment is often referred to as the carbon snake experiment, one of the most spectacular chemistry experiments. Can you now predict what would happen if concentrated sulfuric acid was added to blue crystals of copper sulfate pentahydrate? Well, the acid would drive away water molecules from the salt, resulting in the formation of white anhydrous copper sulfate powder. To sum up, we have studied that concentrated sulfuric acid is a diprotic acid. On reaction with carbon, it liberates nascent oxygen. Uses of sulfuric acid. Sulfuric acid is used in the preparation of explosives like trinitrotoluene, TNT. Sulfuric acid is used in the car batteries.
Atomic radius and the halogen elements. During the topic on
Laboratory preparation of chlorine. Arrange the apparatus as shown in this setup. Take a round bottom flask containing an adequate amount of manganese dioxide. Add concentrated hydrochloric acid through the thistle funnel into the flask. Heat the reaction mixture over a burner. Manganese dioxide reacts with the hydrochloric acid to give manganese chloride along with water and chlorine gas. The reaction proceeds with a brisk effervescence, frothing, and chlorine gas is liberated. This liberated chlorine gas is not pure. The chlorine gas passes through the delivery tube along with the impurities such as hydrogen chloride and is bubbled through the jar filled with water. Hydrogen chloride gets dissolved in water. Simultaneously, some of the chlorine gas also gets dissolved in water, forming hypochlorous acid. The solution of chlorine gas into water continues until the water becomes saturated. The chlorine gas which emerges from the jar is wet due to the presence of water vapor in the gas stream. It is further purified by passing it through another jar filled with concentrated sulfuric acid. Concentrated sulfuric acid acts as a drying agent. It absorbs the moisture present in the chlorine and dries the gas. Since chlorine is heavier than air, it is collected by the upward displacement of air. Electrolysis of aqueous sodium chloride, brine. Sodium chloride, or sea salt as it is commonly called, is readily available to us in plenty, dissolved in sea and ocean water as brine. The electrolysis of Let us study the electrolysis of a saturated brine solution in the virtual lab and the important products formed therein. Take a look at the electrolytic cell filled with brine. Add a few drops of universal indicator solution to it before carefully securing the lid of the cell. The color of the indicator changes to green, indicating that the solution in the cell is neutral. There are two electrodes, a steel cathode and a titanium anode. A diaphragm made electrons move towards the positively charged anode. Here, they lose electrons and form chlorine atoms. Two such chlorine atoms combine to form greenish chlorine gas, which can be seen bubbling at the anode. The color of the solution around the electrode initially turns red and is then bleached to colorless. This indicates the presence of chlorine. As chlorine is getting discharged at the anode compartment becomes richer in Na+ ions. These Na+ ions can seep through the asbestos diaphragm into the cathode compartment. Meanwhile, a lot of activity is also happening in the cathode compartment. Electrons enter into this compartment through the cathode. Water molecules in this compartment accept electrons and form hydrogen gas along with OH- ions. While the hydrogen gas escapes out, the hydroxide ions get attracted by the Na+ ions migrated from the anode compartment, forming sodium hydroxide. The formation of sodium hydroxide causes the indicator solution to turn purple in the compartment. The solution in the cathode compartment is thus an aqueous solution of sodium hydroxide and sodium chloride, which is commonly called caustic brine. No wonder this experiment is correctly termed as colorful electrolysis. The caustic brine from the cathode compartment is concentrated by evaporation, wherein the sodium chloride present in the solution crystallizes first, as it is less soluble in water as compared to sodium hydroxide. Crystals of NaCl are separated from the solution by filtration, and sodium hydroxide solution is collected as the filtrate. We have thus obtained chlorine gas at the anode, hydrogen gas at the cathode, and sodium hydroxide solution as a byproduct of the cathode compartment. An aqueous solution preparation of HCl. Hydrochloric acid. The acid your stomach produces naturally for the digestion of food. And that which is used for pickling of steel is a versatile chemical. It is also an important chemical reagent used either for performing acid-base titrations or for digesting samples for chemical analysis. Let's study how this versatile. Take a round bottom flask with some sodium chloride solution in it. Now, add concentrated sulfuric acid to it through the thistle funnel. Start heating the mixture. Sodium chloride reacts with concentrated sulfuric acid at temperatures below 200 degrees Celsius and displaces a hydrogen atom from H2SO4 to form NaHSO4, sodium bisulfate and hydrogen chloride. Hydrogen chloride and water vapors pass through the delivery tube into the concentrated H2SO4. Which acts as a drying agent and absorbs all of the water vapors. The dry hydrogen chloride moves out and is finally collected by the upward displacement of air in a gas jar. If we continue heating, raising the temperature to about 300 degrees Celsius, NaCl further reacts with sodium bisulfate to form Na2SO4. That is, sodium sulfate along with a molecule of HCl. This sodium sulfate deposits on the walls of the round bottom flask and hinders further reaction. Thus, it is important to maintain the temperature of this reaction below 200 degrees. To sum up, we have studied that HCl Inter-Halogen Compounds. Oils and fats are designated different iodine numbers, which are a measure of the degree of unsaturation in their respective molecules. In analytical chemistry labs, we use Widge's solution, a solution of iodine monochloride in glacial acetic acid, to determine the iodine number of any oil, fat or wax. To understand the underlying principle, have a look at an iodine monochloride molecule. It consists of a covalent bond between iodine and chlorine atoms, both of which are halogens. Such compounds formed by bonding between different halogens are called Inter-Halogen Compounds. However, there is a considerable electronegativity difference between iodine and chlorine, and hence this bond is highly polar. Eventually, it breaks to generate I+ ions, which can further attack the sites of unsaturation in the substrate fat molecules. Let us learn more about the chemistry of inter-halogen compounds. Most inter-halogen compounds like iodine monochloride, chlorine trifluoride, bromine pentafluoride, iodine heptafluoride can be denoted by the general formula XYN, where X is the less electronegative of the two halogens and is named first. N can take values 1, 3, 5 or 7, and accordingly there are 4 classes of inter-halogen compounds. These 4 classes of compounds adopt interesting molecular geometries which can be explained by the VSEPR theory. Diatomic Inter-Halogens. The diatomic inter-halogens have only shared electron pair between the halogens, are hence linear. Bromine monofluoride, iodine monofluoride are a few examples of such compounds. Tetra-Atomic Inter-Halogens. In tetra-atomic inter-halogens, there are a total of 5 electron domains around the central halogen atom, 3 of which are bonding electron pairs and 2 are non-bonding electron pairs. According to the VSEPR theory, the electron geometry of this molecule is trigonal bipyramidal. The 2 lone pairs will occupy the equatorial positions to minimize lone pair and bond pair repulsions, which are greater than the bond pair repulsions. In addition, the axial fluorine atoms will be bent towards the equatorial fluorine in order to minimize the lone pair bond pair repulsions. The shape would be that of a slightly bent T. Bromine trifluoride and iodine trichloride are a few inter-halogens belonging to this class. Hexaatomic inter-halogens. Bonding in such molecules reveals the presence of a total of 6 electron domains around the central atom, depicting an octahedral electron geometry. However, one of these domains at the axial position is occupied by the non-bonding electron pair. Thus, the molecular shape of such inter-halogens is square pyramidal. Cl, F5 and IF5 are a few examples of this category. Octaatomic inter-halogens. Consider the IF7 molecule as an example. There are 7 bonding pairs of electrons. As per the VSEPR theory, they get oriented as a pentagonal bipyramid to minimize the repulsions between these pairs. Let us now discuss the reactivity of inter-halogen compounds. Of the halogens and inter-halogen compounds, which one do you think will be more reactive? Clearly, the bond between the inter-halogen is polar and hence weaker than that between 2 similar halogens. Thus, inter-halogens are more reactive than halogens. Summary. Compounds formed by bonding between different halogens are called inter-halogen compounds. There are 4 classes. Noble gases. We've all observed multicolored and glowing signboards help businesses to draw the attention of customers. So what's the chemistry behind such bright lights? These lights are caused when an electric discharge is allowed to pass through a gas under low pressure in a sealed tube. Orange-red light is obtained by exciting the neon gas, and the blue-green light is emitted by argon. Both neon and argon constitute an important group in the modern periodic table of elements. Helium, which has an electronic configuration of 1s2. The other noble gases have an electronic configuration ending with xenon fluorine compounds. In the period
1937 as the German passenger airship LZ-129 caught fire. This was caused due to the leakage of hydrogen gas used as fuel. Later on, hydrogen was replaced by helium in all such airships, as helium is a noble gas. What are these noble gases and what makes them unreactive? Let us explore the electronic configuration of all noble gas elements. This is a helium atom. Its configuration is 1s2. Let us now
xenon fluorine filled xenon and radon. As the noble gases are characterized by completely filled NS2 NP6 electronic configuration in their valence shells, it requires quite a large amount of energy to remove electrons from the outermost shells of these atoms. Also, the positive values of electron gain enthalpies reveal that these atoms have almost no tendency to accept electrons. One would thus conclude that noble gas elements will not enter into any kind of chemical combination. This was considered true until 1962, when Neil Bartlett became successful in mixing xenon with platinum hexafluoride at 77 Kelvin to prepare xenon hexafluoroplatinate, a red-colored crystalline solid. After this discovery, a large number of xenon compounds with highly electronegative elements like fluorine and oxygen have been prepared. In this topic, xenon reacts readily with fluorine under appropriate conditions to form 3 binary fluorides. At 673 Kelvin and 1 bar pressure, when there is an excess of xenon in the reaction mixture, xenon difluoride is formed. At 873 Kelvin and 7 bar pressure, xenon and fluorine react to form xenon tetrafluoride. At 573 Kelvin and a pressure of 60 to 70 bar, xenon and fluorine react to form xenon hexafluoride. As you can observe, all the xenon fluorides are colorless crystalline solids. Observe the molecular shapes and electron geometries of all the 3 fluorides. While XeF2 is linear, XeF4 is square planar, and XeF6 is distorted octahedral. This is in accordance with the VSEPR theory, as there are 2, 4, and 6 bonded pairs in each of these fluorides respectively. Let us now study a few significant chemical properties of xenon-fluorine compounds. Heating lower fluorides with fluorine gas under pressure results in the formation of higher fluorides. Reaction with hydrogen. Xenon difluoride reacts with hydrogen gas to form hydrogen fluoride and xenon gas. Similarly, xenon tetrafluoride and xenon hexafluoride also form a mixture of hydrogen fluoride and xenon. As fluorinating agents, observe the reaction of xenon difluoride with sulfur tetrafluoride. Fluorine atoms from XeF2 combine with SF4 to form SF6. In other words, xenon difluoride fluorinates SF4 to SF6. Hence, it behaves as a fluorinating agent. Reaction with water. Xenon fluorides must be carefully stored away from water as they are readily hydrolyzed even with traces of water. Let us study the reactions of xenon fluorides with water. XeF2 is soluble in water but undergoes slow hydrolysis, evolving O2. XeF4 giving xenon EF6. To sum up, we have studied that xenon combines with fluorine to form xenon oxides, structure and hybridization. Objective. In this topic, we will study the structure and hybridization of the two xenon oxides. Let us begin with xenon trioxides. Observe the molecular view of XeO3. There are a total of 14 electrons in the valence shell of xenon, 8 of which are from the xenon atom and 6 from the 3 oxygen atoms. This implies that there are a total of 7 electron pairs to be accommodated around xenon. To understand the geometry of XeO3, let us study the hybridization in xenon. In the ground state, xenon has an outer electronic configuration. Note that there are no electrons. 5e10 has an outer electronic configuration of krypton. 4d10, 5s2, 5p6. Note that there are no electrons in the 5d orbitals of xenon. In the excited state, 3 of the 5p electrons jump to the empty 5d orbital. In order to accommodate 7 electron pairs, the 5s and 3 of the 5p orbitals intermix to form 4 sp3 hybrid orbitals. One of the sp3 hybrid orbitals is occupied by the lone pair of electrons. The other 3 sp3 hybrid orbitals of xenon are half-filled. 3 oxygen atoms with outer electronic configuration 2s2, 2p4 approach these half-filled orbitals of xenon. One of the half-filled 2p orbitals of each of the 3 oxygen atoms overlaps the other 3 half-filled sp3 hybrid orbitals of the xenon atom. Recall that there are 3 unpaired electrons in the 5d orbital of xenon. Notice that each of these oxygen atoms still has a half-filled 2p orbital, each of which overlaps with the half-filled 5d orbital of xenon to form pi bonds. As xenon undergoes sp3 hybridization, the electron geometry of the molecule is tetrahedral, as one of the corners of the tetrahedron is occupied by a lone pair. The shape of the molecule is pyramidal. Let us now study the structure and hybridization in xenon tetroxide. In this case, the orbital view comprises of 16 electrons in the valence shell of xenon, 8 of which are from xenon, and the other 8 belong to the 4 oxygen atoms. Thus, there are a total of 8 electron pairs to be accommodated around xenon. Recall here the ground state electronic configuration of xenon is krypton 4d10, 5s2, 5p6. Note here that there are no electrons in the 5d orbitals of xenon. In order to accommodate the 4 oxygen atoms, 1 electron each from the 5s and 3 of the 5p orbitals get excited to the 5d level, and the 5s and 3 of the 5p orbitals intermix to form 4 sp3 hybrid orbitals, each of which has a single electron. 4 oxygen atoms, each having outer electron configuration 2s2, 2p4, approach these half-filled orbitals. One of the half-filled 2p orbitals from each of the oxygen atom overlap with the 4 sp3 hybrid orbitals to form 4 sigma bonds. The other 4 half-filled 2p orbitals overlap with the 5d orbitals of xenon to form 4 pi bonds. Due to sp3 hybridization, the molecule is tetrahedral in shape. Summary: we have studied the following explanation of